So, we've all seen what generative AI can do, right? It can write an email, it can whip up an incredible picture of an astronaut riding a horse. But what if an AI could generate reality itself? Today, we're diving into something truly revolutionary, a technology that's learning to understand the fundamental laws of our universe, generative physical engines.
To get why this is such a massive deal, let's just start with a super simple test. Look at this. Which ball hits the bottom first? A toddler could figure this out just by playing, and most of us intuitively know, yeah, it's the ball on the curved ramp. It just builds up speed way faster. Seems obvious, right? Well, this exact question trips up some of the most powerful AIs in the world today. And this is what we call the intuition gap. You ask a leading large language model, and it gives you an answer that sounds really scientific, really plausible, but it's totally wrong. It just misses the whole nuance of how forces work over a path. And that's exactly why we need a new kind of AI. We need one that doesn't just parrot language about physics, but one that actually gets physical reality. Okay, so to really appreciate this huge leap forward, we first have to talk about the villain of our story, the old way of doing things. For decades, yeah, we've been able to simulate physics, but it's always relied on this incredibly slow, brute force method.
Welcome to the world of traditional solvers, things with names like computational fluid dynamics, or CFD, and finite element analysis. Basically, these methods take a digital object, say a car, and they have to break it down into this complex mesh of millions, sometimes billions, of tiny little points. And then the computer has to painstakingly calculate all the forces on every single one of those points, one tiny fraction of a second at a time.
And yeah, the whole process is just as slow and painful as it sounds. First, you build your 3D model. Then you hit the major bottleneck, creating that insanely complex mesh, which takes forever. Only then can the computer even begin its step-by-step calculation. And the result? You wait, and you wait some more. We're talking hours, often days, for a single result to come back. But now there's a new hero in town, Generative Physical Engines, or GPEs for short. And let me be clear, this is not just some small upgrade. This is a complete paradigm shift. It's like we're giving the AI a kind of digital intuition. So here's the absolute game changer. GPEs completely throw out that slow step-by-step method. Instead of calculating every single millisecond of a process, they're trained on mountains of simulation data to learn the direct connection between the start of a problem and its final stable end state. You can almost think of it like a generative prompt. The initial conditions are the prompt, and the AI generates the final physical outcome, all in one shot. The fancy technical term for this magic is direct boundary to equilibrium mapping. It's this incredible ability to just jump straight from the beginning to the end, the final stable solution. This lets it completely bypass all that sequential time stepping that makes the old solvers so slow. And here's the other cool part. It also gets rid of the main source of errors. See, in the old method, tiny little mistakes would just pile up with every single step. GPPs don't have that problem. They just leapfrog over it all. This chart really just lays it all out. I mean, look at the difference across the board. The core method goes from that slow, iterative solving to instant generation. Simulation time, it drops from hours or even days to just seconds or minutes. That dependency on creating a mesh, basically gone. And error accumulation, minimal. It is a complete reinvention of the whole process from top to bottom. And what does all of that add up to? How about this? 1,000 times. On average, GPSers are 1,000 times faster than the traditional solvers they're replacing. That's not just a little better. That's a whole different reality. 1,000 times speed up sounds almost unbelievable. But what does that actually mean for us in the real world? This is where we get past the how and into the so what. And trust me, the possibilities this unlocks are pretty mind-blowing. Okay, let's make this real. Imagine a super complex 3D model, the kind that a traditional solver would have to break down into over 200 million separate little cells. A GPE can simulate that entire thing in under 100 seconds. A task that would have tied up a supercomputer for days now happens in less time than it takes to brew a pot of coffee. And this power is already hitting entire industries like a tidal wave. In Formula One racing, engineers can now test hundreds of new designs in a week, not just one. In Hollywood and video games, artists can create perfectly realistic fire, smoke, and water in real time. We can build digital twins, perfect virtual copies of real-world things like a city's power grid that can optimize themselves on the fly. In robotics, you can safely generate millions of training scenarios so robots can learn physical tasks. And climate scientists? They can now run massive sets of weather models to get way better at predicting hurricanes and other extreme weather.
But, okay, like with any game-changing technology, the work is not done. We've got to ground the hype for a second and look at the huge hurdles we still need to clear for GPUs to reach their absolute full potential.
And believe me, the motivation to solve these challenges is massive. We're talking about huge economic stakes. The generative AI market is expected to absolutely skyrocket from around $40 billion today to nearly $900 billion by 2032. GPEs are a massive piece of that pie, and whoever cracks these next problems is going to define the next decade of science and engineering.
So what's the biggest barrier right now? Well, it's something called generalization. Today's AIs are amazing at what's called local generalization. They can handle new problems that are pretty similar to what they've already seen in training. But we humans are capable of extreme generalization. We can think about totally new, crazy situations we've never seen before. A GPE trained only on cars driving on a highway might completely fail if you suddenly ask it about a hypersonic jet. It just can't leap to physics it hasn't been trained on yet.
And that leads us to the final and maybe most important mandate: trust. Before we let an AI design the wing of a plane you and I are going to fly on, we need to know exactly how confident it is in its own answers. The technical term is uncertainty quantification, or UQ. It's not enough to get an answer fast. We need to know the probability that the answer is right. For anything mission critical, this is completely non-negotiable.
Which brings us to our final and kind of mind-bending thought. This whole journey started with just trying to make simulations faster, going from brute force math to AI-accelerated physics. But the ultimate goal? That's something way more profound: AI-discovered physics. The question we're facing now isn't just can we make it faster? It's will these systems, by learning the deep patterns of the universe from pure data, one day show us fundamental laws of physics that we, their creators, never even knew were there? Now that is the truly revolutionary promise of all this.